concept of hypothesis testing, we can work with it in proportions. So let x1 through xn be a random sample of size n from a binomial distribution with probability, or with n and p as our two parameters, as we've talked about with the discrete distributions. Case 1, how do you structure your hypothesis testing? Well, the null hypothesis is that the true probability of success p is equal to some value, a specified value, against an alternative hypothesis. And this is just like I had a moment ago. The true proportion is less than this specified value. That could be one alternative. That could be your alternative that you're testing against. Your alternative could be that the true proportion is higher than that number. Or your third alternative is that the true proportion simply isn't equal to that number. So depending on your interest is what you'll have, is how you'll determine what your alternative hypothesis is. At a alpha times 100% level of significance, calculate the value of a test statistic using x random variable following a binomial distribution and with a probability of success p is equal to the specified value. Find the number of successes and compute the appropriate p-value. Depending upon the alternative hypothesis, whether it's less than p naught, greater than p naught, or simply not equal to p naught, and reject the null hypothesis, if the p-value, again, the p-value is determined from the sample results, is less than alpha, your indicated level of significance. So we have, actually I think it's better if I just go, it goes better if I show you the numbers on this. That's going to be if the small sample sizes. If you have large sample sizes with p not extremely close to 0 or 1, then what you're testing is test the null hypothesis, again, just as we had before, that it's equal to some specified value. And you have to look and think about, well, what is my alternative? Is it I believe the true proportion is less than the null hypothesis, greater than the null hypothesis, or simply that the true population proportion is not equal to the specified value p naught. So for a large sample size, what we're going to be doing is using the normal approximation to binomial in the hypothesis testing. And again, the section in your textbook, you can go back and refer to it, but with large N, you can use the normal distribution as a good approximation of the binomial distribution. So again, we've gone through quite a bit of binomial distribution when N was equal to 15 or N was equal to 10 or whatever. We use small n, but suppose N instead is 400. Suppose N is 2,000. And so this is when normal distribution gives a good approximation for figuring out what are those probabilities. So in this case, n times p is, you're going to be working with mu is equal to n times p naught, and the variance is going to be n times p times 1 minus p. And then in the case, since we're dealing with large n and we're saying that normal is a good approximation, then we could turn our attention to the z-score and say x, the observed number of successes, minus the mean, n times p naught, divided by the standard deviation to determine how many standard deviations away from the mean is the x from n times p. And then we're going to reject the null hypothesis if the associated z-value is less than the z alpha, for an alternative saying that the proportion is less than, the real proportion is less than the hypothesized one. Or we'll reject the null hypothesis if the z-score, if this calculated z-score from your test results comes out to be greater than z alpha. And then we'll also reject the null hypothesis if you're doing a two-sided test. So let's look at an example. Back to the missile manufacturer who claims the probability of success for a missile MX is 0.80. To demonstrate its reliability, 15 missiles are fired. If 9 are successful, do you agree with the manufacturer's claim? Based on this information, we'll set up a test that says, okay, our null hypothesis is that, as the manufacturer says, it's 0.80. And the alternative, we'll do a two-sided test and say that the proportion, the probability of success for a missile is not equal to the 0.80. So it could actually be less, could be more. The test statistic X is X, the observed number of successes. And so we're looking, 15 are fired, and X, we're going to be looking, and that can be, what could have happened is none fired successfully, 1 fired successfully, 5 fired successfully, all 15 could fire successfully, right? And so we looked at it and said, okay, on this particular one of 15 missiles, 9 fired successfully. So alpha over 2, a two-sided test. We're going to go ahead in this case and though it wasn't stated, where do we have 0.025? So we're going to run with an alpha equal to 0.05. Should have said that on the previous slide. So test this on with an alpha of 0.025, or 0.05 rather, 95%. The level of significance is 5%. And so two-sided test, right? Could be that the proportion is much less than 0.80. Could be the proportion is much greater than 0.80. We're not saying one way, we're just noting that it's not equal to 0.8. And so we look and say, okay, we're looking for two cutoffs, basically, a lower one and an upper one. And we're looking, in this case, this is a little bit different kind of problem. We're looking to see what are the probabilities, what's the value of L such that the probabilities add up to alpha over 2 for all values X less than or equal to this number L. L is what we're trying to find. And what's the value of U such that all possible outcomes of X above U, the sum of those probabilities would also add up to alpha over 2. And if we solve these two, given the fact that N is equal to 15, probability of success is presumed to be 0.80, and probability of failure, therefore, is of 0.2. And we solve that to find that the lower number is 8, and you end up with a 0.018. And there's no value for U such that the values you add up and you'd have a value of 0.025. No values over U to 15 that add up to 0.025. So if we reject the null hypothesis if X was less than this value L, 8, and since X is equal to 9, we would accept it and conclude that 5% with 5% level of significance that the manufacturer's claim is correct. Okay, again, we're going to probably go through some better examples in class than that one. Okay, second one. A manufacturing company submitted a claim that 90% of the products of the items produced by a certain process are non-defective. An improvement in the process is being considered that they feel will lower the proportion of defectives below the current 10%. In an experiment of N equals 100 items, didn't say the N, but that's what's implied here, large sample size, are produced with a new process and 5 are defective. Is this evidence sufficient to conclude that the method has been improved? Use a 5% level or a 0.05 level of significance. So we know that we're working with a large sample size, and we're going to use the normal distribution as a good approximation for the probabilities associated with a binomial. Our null hypothesis is that the claim that 90% of items produced by a certain process are non-defective. That's our null hypothesis. That is 90. We're putting in a new process, manufacturing process, with the hope that the non-defective yields, will be higher than 90%. So alternative in this case is going to be that P is greater than 90. Alpha is equal to 0.025. Critical region for, and again, it's a one-sided test. So Z of 0.05 is 1.645. And so our critical region is defined as if we get any test statistic, we're going to calculate our test statistic. If it's greater than 1.645, then we're going to reject the null hypothesis that the number of defectives is 90%. So we do our computation. X, the number of items that were successes, so to speak, 95 out of the 100. The mean of this then would be n times p naught, which is 100 times 90, 0.9, which gives us the 90. So how far above is 95 from 90 in terms of standard deviations? 100, n is 100, p is 0.9, 1 minus p is 0.1. And so what we see with for this particular sample, the z-score turned out to be 1.67, which indeed is greater than the 1.645. That was our cutoff that we said, okay, we would accept the null hypothesis if that test statistic had turned out to be less than or equal to 1.645. But in this case, the 95 led us to 1.67, and that is certainly greater than 1.645, so therefore we reject the null hypothesis and conclude that an improvement has been made. Okay, so this is a brief look into what I call parameter, I think the textbook calls the same thing, parameter hypothesis testing. We're concerned with tests concerning a single mean, tests concerning the difference of means, tests concerning the difference of proportions. And all of those kind of additional topics in this parameter hypothesis testing are in your textbook that you can also look through. And I'm going to cut off now, and in the next recording session, turn our attention to something called the testing for the goodness of fit.